So, very good morning to one and all. So, in this lecture and last lecture, we have seen how the solidification process occurs by a transformation from a liquid state to a solid state. So, during the process of solidification, and we have seen that each nucleus, so first thing we can observe in a solidification process is a nuclear formation, isn't it? So, each nucleus after it is formed, it undergoes the next step would be the growth. So nucleation, growth, and final crystallization will come to an end. So each nucleus grows by attracting atoms from the liquid metal into the space lattice. So each nucleus grows by attracting atoms from the liquid metal to the space lattice. And you may please note that the crystal growth, which continues in three dimensions, the crystal growth continues in three dimensions. I mean the atoms attaching themselves in certain preferred directions, usually along the axis of the crystal, and it will give rise to a characteristic tree-like structure which is called the dendrite. Okay, that's called the dendrite. Now, if you look at this diagram, you can see that the different dendrites have formed up. All these represent different dendrites. So when we are allowing the molten metal or the liquid metal to solidify, here in this container of liquid metal, here uh, liquid metal starts solidifying. I mean the nucleus starts forming. Here another nucleus starts forming. Here another nucleus starts forming. Here another. So all these points, the nuclei start forming, and you may please note that the each nucleus is formed by chance. You can see that the crystal axes are pointed at random. If this is a crystal axis, you can see that all the crystal axes are pointed randomly, and you can see that the branches, I mean the dendrites growing out from them, will grow in different directions in each crystal. So this is a dendrite, this is a dendrite. So what would be the initial product is nothing but the nuclei formed, and for all the nuclei, when it is converted to a crystal by adding more and more atoms, and if you take the axis of that small particular crystal, and if you take the infinite number of such crystals in this here, and you can see that all the crystal axes are pointed random. Okay, and this is something like a crystal skeleton, I will say, from which, so if you take a single dendrite, it's like a crystal skeleton, I will say. So here you can see that there is a primary axis, or there is a crystal axis from which the arms begin to form. I mean the arms begin to grow in all directions depending upon the lattice pattern. So for example, if you take this dendrite, there is a primary axis, and you can see these are the secondary axis. Maybe this small one as the tertiary axis, for example. So which means from the primary arms, the secondary, tertiary, etc. arms begin to sprout. So why I say sprout is it's somewhat similar to the branches and twigs growing out of the trunk of a tree. You know the tree with different branches and sub branches, isn't it? So okay, so this is a all individual dendrite is analogous to a crystal skeleton, I will see. Okay, and you may please note that at the same time the dendrite grows, the dendritic arms. So they are these dendritic arms. I mean, this may be the small secondary and tertiary arms. They thicken at the same time. I mean, the dendritic arms continue to grow and thicken at the same time. The dendritic arms grows and more atoms are deposited and it also thicken at the same time until ultimately the space between them will become filled with solid. Okay, now so actually likewise a dendrite is formed at a particular point, another dendrite is formed here, another is formed here randomly at all places. So how this dendrite is formed from a nucleus, initially a nuclei formed and to that an atoms are attached, and likewise the different branches are sprouted from the trunk of a tree. Each dendrite is formed, and soon after some time you can see that, for example, this tertiary arm of this dendrite, maybe this tertiary arm of this dendrite, that will make contact with, I mean, the one dendrite begin to make contact with the neighboring dendrite, and finally you will get a structure like this. Okay, so this is actually a schematic diagram for a dendritic crystal formed by three-dimensional dendritic growth. You can see this as the primary axis, this is the secondary axis, this small one as the tertiary axis, and finally you will get a structure something like this. Okay, now if you look at the uh, if you look at this diagram, so what is shown here is the temperature versus time, that is a cooling curve. So which means when a molten metal is allowed to cool and how the solidification process takes place is shown by this graph. The temperature taken on the y-axis and the time is taken along the x-axis. You can see that as the temperature of the molten metal brought down, the solidification process begins. Now you can see a small well here, or a small crater like shape. So this is nothing but the undercooling which is done to driven to drive the solidification process. Okay, now these are the what is shown on the right hand side is a different stages in the solidification of crystalline materials. You can see, look at this diagrams, schematic diagram. For initially some nucleus are formed at the different parts of the container. For example, this is a cavity or the container to which the molten metal is poured, and then it allowed to solidify. When it is allowed to solidify, you can see that at different parts of the liquid metal the nucleus starts forming, and this nucleus once started formed at different points, atoms are added up and it converted to growing crystals, and then it forms as a dendrite, and from the dendrite it you can see this is a final crystal which is formed. You can see different grains which are separated by grain boundary. So these are the various stages in the solidification of crystalline material during the solidification process. Okay, now this is the point where we are interested, though we are interested in these three phases, but we are very much interested here as a mechanical engineer. You are interested in this last picture. Okay, the last one. You can see the final solid is obtained, where you can see that different grains, and these grains are separated by grain boundaries. Now, if so, this is the area of interest for a material or a mechanical engineer, I will say. So here, what is meant by a grain is a portion of the material within which the atomic arrangement is nearly identical. If you take this particular grain, this is grain number 1, 2, 3, 4, 5, 6, 7, different grains. It's a combination of grains, you will get a final solid. So if you take a single grain and you can find the atomic arrangement is nearly identical. But if you take two grains, so may grain 1, 2, 3, the orientation of the atomic arrangement is different. This grain is oriented differently than this grain, or this is oriented differently than this grain. So this point is very important. Okay, and another important point I would like to tell you, the area. So maybe it is drawn like a 2D image. Actually, it's a 3D one. Okay, when you know that when a crystalline solid is formed, how it is formed. Okay, so I can say the area along which the grains meet. The area. So this is actually a 2D image. So you will view like a 3D one. So the area along which the grains meet is called the grain boundary. The area along which the grain meet is called the grain boundary. It's called the region of mismatch because the atoms at the grain boundary are irregularly placed. This is actually a scanning electron microscope image of a grain boundary. You can see that these are the different grains. So you can see that the resolution of this image, and you can see, so this is actually a transmission electron microscope where you can see the resolution in the nanometer range. And when you look at this, you can see that this is actually the grain boundary. This is a grain, this is a grain. Look at the grain. This is, let us imagine, let us say this is grain 1 and this is grain 2. Look at, if you look at the grains, you can see that if you take grain 1, the arrangement of atoms in grain 1 is almost similar. You have a atomic arrangement is nearly identical in each grains, but the orientation of two grains, if you take, they are different, and they are separated by an area. They are called the grain boundary. Okay, thank you.